205. Okay, so y is equal to 2 to the third.
You said 44
Yeah.
on 205. Okay, y equals?
No, I'm sorry. 2 to the third to the x to the second. Keep on going up.
Very good.
So in this instance,
Yeah, we haven't talked about this formula. This is a differentiation rule that I would like to start with right now. So forget about the problem for a second. If I differentiate e to the x, what do I get? Right. If I should, to be exact, I should multiply by natural log e. And also I should multiply by x prime. Why don't I do that? Because this is 1 and because this is 1. Okay. Now, e to a function prime is e to the function times the function prime, which is very clear. Now I have to put it in. And it should be times natural log e, but again, I don't put it because it's 1. By the same token, when I have any other base, not e, and I differentiate, I have a to x times natural log a. This time it has to be there. It's a constant, but it has to be there. Why? Because natural log a is not 1. The same thing when I have a function, a raised to a function of x. This will be a raised to the function, of course times the function prime, but still times natural log a, because natural log a is not 1. And now we are ready to look at that example, which is 2 raised to 3, the third power, which is raised to x squared. So y equals 2 raised to the third power, which is raised to x squared. Please try to understand that the best thing to do is decompose, at least in your mind, decompose this function. So first of all, I see 2 raised to a power. So how do I differentiate 2 raised to a power? Is 2 to that power, and I will put it in a minute, times that power prime times natural log 2. So this is the first step. So a to a power prime is a to a power times the power prime. If it's just x, then it's just 1 times natural log 2. Now I look at the power. So I copy the power, and in here I copy 3 raised to x squared prime, because I like to do it in 2 steps. This is not as straightforward as the other ones. Okay, now this is done, but I have to differentiate this. So equal symbol, 2 raised to 3 raised to x squared times. So again, I have the same formula. I'm differentiating 3 to a power. So when I differentiate that, I have 3 to that power. Now I'm almost done. It's times the inner function prime, which is 2x, but I cannot forget that this was not e. So I have to multiply by natural log 3, and of course I have to copy what I had before, natural log 2. Very good pick. Does it make sense?
can we go through that?
Yes.
The very last part.
Yes. So is this understood and this understood? Okay. I'm applying the same formula here. So 3 raised to x squared prime is 3 raised to x squared times the inner function prime, which is 2x, times natural log 3 because the base is not e. So 3 raised to x squared times the inner function prime, which is 2x, times natural log e. So this is these 3 factors.
Okay.
Then I copied this and I copied that. So the same formula. 3 raised to a function prime is 3 raised to a function times the function prime times natural log 3 because the base is 3. Better?
Yep.
Okay, perfect. Thank you, Derek, for bringing this to class. Anything else? Anything else?
Just in general, how many sections do we plan on going through before we get spring break?
Oh, I'm not sure. I'm not sure. So we haven't finished the chain rule. So I have to present more problems on the chain rule. I think we should look. I mean, we looked at a few things, but I still believe I owe you a few more problems. Then we have to look at implicit differentiation. Then we have to look at log functions. And then applications. So maybe we finish this before spring break. We do not cover 3.8, but then 3.9, 3.10, and 3.11 would be after the spring break. So maybe till the 3.8, but 3.8 is not covered. So this is 3.4. 4, 5, 6, and 7. We'll see. Good. Is this clear now? Better? Okay. Other questions for me? Anything else you'd like to go back to? Anything? 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 So I'm going back through the notes for a second and see how many more problems you think. So this was not the chain rule. So we only had just a couple of problems. One with a rational function, and the other one with an exponential. This one with a base other than e. One with a square root, and one kind of intense. This is intense. This is not a friendly function at all. And then the word problem. You feel like working on more problems with the chain rule? I mean, the chain rule is not going to disappear. Moving forward, we have the chain rule all the time. Do you feel like more chain rule, or we continue with implicit differentiation? Yes, please.
I guess maybe like one more, maybe a rational chain.
Yes. Yes, let me show you, or if you have your book. Yes, of course. Let's do just that. I mean, the next step, implicit differentiation, that's exactly what it's going to have, but please choose anything. Maybe you want, I don't know. We did this problem 26. This is extremely important. We can choose one maybe from the end of the chapter. Maybe there is something interesting in there. This is horrible, absolutely horrible, because it has the denominator that is also a product. I'm not going to, this is a problem for homework. It's going to take 15 minutes to me to work on that.
Something similar is fine. I mean, I think number 11 or on the previous, yeah.
This one?
Yeah.
Okay, this is really easy. So we can spice it up and put something else at the top, if you'd like. Because this is not exactly the chain rule, basically.
Okay.
Yeah, that's why I'm saying it's not really the chain rule. Yeah, so these will really be chain rule. We did this problem together. Yeah, we looked at this one. So your idea was a rational function. I mean, we can make one up. It's really not a problem. I mean, we can try this one, but just drop one of the factors in the denominator.
That's fine.
And you tell me which one you want to drop. It doesn't matter. Because we don't want to solve a problem in 20 minutes. So Just let me know. You want to drop the first one or the second one?
We'll drop this.
We'll drop the second one. So you want x squared plus 1 to the fourth over 2x plus 1 to the third.
Yeah.
Okay, perfect. So let's look at that. So we have y equals x squared plus 1 to the fourth power and divided by 2x plus 1 to the third. Perfect pick, because you're going to see something like this, not this, this intense, in chapter 4. And you'll see when we use this and why. We made one up. It's a combo, actually. So I can tell you it's a part of problem 30 on page 265. But not exactly. We massaged it. Okay, so when we differentiate a quotient, you can already write the denominator, which power, because we do not differentiate the denominator. Over there in the denominator, I meant. So what power will you take the denominator to? Yes, of course. Because you have this squared. Copy the base, multiply the exponents. Now the numerator, remember, has to have a difference. If you don't have a difference, something is wrong. And the order is very important. So the top function prime is bring down the power, subtract 1 from the power, and times the inner function prime, which is 2x. Thank you. But then I have to multiply by 2x plus 1 to the third. Then minus, I copy the numerator, and now I differentiate the denominator, which is 3. 2x plus 1 squared multiplied by 2. Now the key step is now, which means if you try to simplify, there will be a terrible mistake. But instead, we have to factor out maximum possible. So I see a 2, this is a 3 and a 4, so 2 is coming out, this one. Then an x squared plus 1, but I have to decide upon the power. This one has 3 and this one has 4. So what will be the power that comes out?
3.
Yes, always the smallest. Perfect. Also, I have 2x plus 1, and this has 3 and this has 2. Which power comes out? 2. Remember, there is a subtraction in there, so we have to have a difference, right? Okay, so then what is left from the first one? The 2 is out, but there is an x left in there. The 4 is also left inside, because 2 is out, but x and 4 are in. X squared plus 1 to the third is completely out, but 2x plus 1 to the third and 2x plus 1 squared, we have a 2x plus 1. 2, go ahead.
Can we factor out 2?
Yes, this 2 and this 2, but not the 4.
Okay.
So I still have a 4x. I have a nothing from here, but a 2x plus 1.
How would it not be 2x? Like, you factored it out. I'm a little bit lost on that. Yeah.
So what's the question?
So you took out a 2. Why wouldn't it become the 4 that's in front of the 2x plus 1? Why wouldn't that just become a 2 then?
Because I'm removing this. I'm not removing that.
Okay.
I'm removing this. A 2 from both of them, not the 4. This should have been 8. So if I remove 2, then I have still 4 in there. Better? Okay. Is everything else okay so far? Okay. So now I have a 3, because this 2 is gone. Now x squared plus 1 to the fourth power, I have x squared plus 1 to the third power outside, so there is an x squared plus 1 left inside. And 3x squared, I'm sorry, 2x plus 1 squared is 2x plus 1 squared out. Now, only now I can do this. Not before. And that's a big step. So then 2x squared plus 1 cubed, and now I distribute. So 8x squared plus 4x minus 3x squared minus 3 over 2x plus 1 to the fourth. And this is 2x squared plus 1 to the third, and I combine like terms, and I have 5x squared plus 4x minus 3 over 2x plus 1 to the fourth. And this is final. And this step is very, very, very useful. Questions, please.
Can you go look up to the top so I can see?
Yes, of course.
I'm sorry, the 2 that you had removed on the far right. Where did that come from?
You mean this one?
Yes.
So I have two terms. If I remove a 2, oh, where it came from?
Yes.
From the inner function prime.
Oh.
2x prime is 2. Sorry about that. I jumped into conclusions. Yes, it's coming from the inner function prime using the chain rule.
Okay.
Better?
Yes.
Good. Do you think we have anything else before we continue with implicit differentiation? And that is section 3.5.
So that 2x came from where? The very beginning of it. 2x that you, yeah.
So for
Yep.
x squared plus 1 to the third times the inner function prime times the denominator
Okay.
minus this and 3 and 2x plus 1 to the second power times the inner function prime. Better?
Yep.
Good. Other questions on this? Brian, is this okay? Is that what you meant?
Yes.
Okay. Good. Other questions here? Anything else? Okay, 3.5, implicit. Implicit differentiation. This is all about the chain rule. You'll see in a moment. Okay, so if I have a function that is f of x e to 5x squared, and I ask you to find f prime, what will you say?
Times 5x squared.
Okay, let's talk about it one more time. So e to a function prime is e to the function times the function prime times 10x indeed. Of course, I'm going to put that in front, so this is 10x e to 5x squared. This is the derivative of this function. And you can say, what's all this? Why are you doing this? And my answer is, I just wanted to say that in this example, I am given the function directly. The function is given to me. It's either f of x or y equals whatever, but it's given directly. Okay. Now, look at the following scenario. And you can say, what is this? And I'm going to say, given this equation, find, I'm not going to write y prime. I'm going to write the notation that we must use here. I shouldn't say must, I take it back. We should be using now. I'm asking you to find dy over dx. You think we can solve this equation for y? Not this lifetime. Absolutely not. A calculator may probably come up with an answer on 5 pages. Another calculator, computer software of the y equals. So the function is given to us, but indirectly or implicitly. So the function is given. It satisfies this equation, but I don't have the function. So y given implicitly through an equation. So that's where the name is coming from. So I can differentiate, but not directly because the function is not given directly to me. It's given implicitly. So I'm going to use implicit differentiation. Meaning, whatever I do to the left-hand side, I have to do to the right-hand side. If I add 5, or divide by 10, or take the square root, or apply a procedure, whatever the procedure is, apply natural log, or who knows. If I do it to the left-hand side, I have to do it to the right-hand side. But there is a catch here, which is very important. In this notation, what am I telling you? Please find dy over dx. What am I telling you? Exactly. Y is a function of x. Y is not a variable. You cannot differentiate 2y squared and say it's 4y. No, you can't. It's a function raised to a power that I need to differentiate. So this is a key concept. Okay, now I'm ready to differentiate the left-hand side. So this is just 2 times the function raised to a power. How do I differentiate this? 4y times dy over dx. This is this differentiated. Now I am looking at the product. So I'm going to copy -3 and I'm going to work on x, y to the 4th. Leave the constant outside. Don't bother with it. This is function number 1 and this is function number 2. I differentiate function number 1, which is x. That's just 1. Y to the 4th plus. I copy x because it's the first function, but now I'm here and I need to differentiate a function to the 4th power. Yes, I have to bring down 4. I subtract 1 from the power, but that's not sufficient because y is a function of x that I don't have. So times, indeed. So all this side is done, now equal symbol. I have to differentiate sign of a function. Start from the outer and go to the innermost. So when I differentiate sign of y, I get very good times the inner function prime, but the function that I don't have. So what is that? Of course. I know it's a mess. It really is. But it's a linear equation now. I'm after this. This is the variable that I'm trying to solve for. But of course I have to clean it up. I have to move the terms with dy on one side and the terms without dy on the other because it's a linear equation in dy over dx. Before we do that, is the step from here clear? Is that a yes or? So 4y times dy over dx minus 3, leave it alone. First function prime is 1 times the second function plus the first function times the second function prime, 4y cubed dy over dx. Then I differentiate sign to get cosine. Sine x prime is cosine x, but this is not x, so I have to write times dy over dx. Is this better? We'll have more examples, of course. This is just the first one. I'll let you choose in a minute. So now I have 4y dy over dx. I will distribute -3 to these two terms, -3y to the fourth minus 12xy cubed dy over dx equals cosine y dy over dx. I see two terms with a variable on one side and one term with a variable on the other. So I'm going to move this to the other side, and I'm going to move this to the other side because it's the only term without the variable. At the same time, I will factor out. I said I would factor out, and I didn't leave room for it. From those three terms, I factor out the variable, which is dy over dx. Can anyone dictate what is left in parentheses?
4y.
That's it. We're done. Of course, now you can say, yeah, what did you accomplish? Nothing. You came up with an expression for dy over dx, but you don't have the function. So what's the use of this? Very important use. So let's write 3y to the fourth. It has a very important application. I came up with this equation out of my left pocket. So I just threw something in there. I don't know if this has any solutions. I really don't. I just made one up. So, but assuming we find a point, I'm just making this up now. And I don't want to use numbers because I can't. I have not checked anything. Let's say a comma b. So I'm not interested really in an expression for dy over dx, but I want you to evaluate when x is a and when y is b. And you will eventually get a number, I guarantee you. I don't have a and b because I have to make sure that a and b, a comma b, verifies the equation. And since I just made that up, I don't even know if it has solutions, right? So assuming that the point a comma b verifies this equation, then I can ask you, find, although we don't have the function, we don't care, we just want to determine the rate of change of y at a particular point. If I have the point, then we can simply determine the number. So now we can pick something legitimate. This was just something I made up. We can pick anything legitimate from all these problems. So I shouldn't say legitimate. They checked them. I just didn't get the chance to check it. So find dy over dx by implicit differentiation. Why? Because no one can solve this. There's no one can solve this for y. No one can solve this for y. Not with those, most of them cannot be solved for y. So the equation is given, meaning the function is given implicitly. So in order to find dy over dx, I will have to differentiate implicitly. What does that mean? Differentiate one side and differentiate the other, and then solve for dy over dx. So would you like to pick, or 1,
About 8.
2? Okay, 8 it is. This one?
Yes.
Okay. 8 on page 215. So is 2x cubed plus x squared y minus xy cubed equals 2. Perfect example. It's a more human example than the one I picked. So yes, very good. Okay, then. No one can solve this equation for y. Don't even try. Not in your wildest dreams. It's not going to happen.
Should we attempt it for extra credit on the test?
Say it again.
Should we attempt it for extra credit?
No. Don't waste your time, please. Good. So the left-hand side is a mess. The right-hand side is? Excellent. Well done. Good. The left-hand side, the first term, when you differentiate, what do you get? So remember, we are asked to find dy over dx, which clearly means y is not a variable, y is a function of x. Differentiate, solve for dy over dx. Okay, ready? 2x cubed prime is definitely 6x squared. There is no problem there. But the following two terms are products of different functions, 1 and 2, 1 and 2. Plus, remember each product, when you apply the product rule, you have to come up with two terms. And then please leave the negative sign outside. Do not try to, unless you're comfortable with that, that's fine too. I would leave the negative outside and apply the product not on the negative, on this difference, but apply the product rule on the positive xy cubed, and then you can distribute -1 later. So then, when I differentiate the first function, I get 2x times y, but then I get x squared times the derivative of y, which is,
What prime?
yes, but we have to write, I shouldn't say we have to, but please write dy over dx. Okay, minus, I differentiate the first function, and I get 1 times y cubed, and plus, I keep the first function, and now, very carefully, I differentiate y cubed. But y is not a variable. Y is a function. So I get 3, careful, y squared times dy over dx, right? I bring down 3, I subtract 1 from the power, and then, so that's why I'm insisting in starting from the outermost function to the innermost function, so you don't miss anything. So 3 in front, subtract 1 from the power, we're still working on the power, times the inner function prime, which is dy over dx. So remember what we are after. This is what we are after. So here I don't have anything to distribute, but here I will distribute -1. So I have 6x squared plus 2xy plus x squared dy over dx. I'm just copying the first three terms. But yes, now I have -y cubed and minus 3xy squared dy over dx equals 0. I didn't do anything. I just copied everything and distributed. I distributed -1. Okay, so I will keep this term and this term, and I'll make these disappear to the other side. At the same time, because I'll try to cut back on writing just a little bit, I will put in parentheses x squared minus 3xy squared and dy over dx. Why? Because I have to pull out dy over dx from these two terms. Then everything else moves to the other side. Y cubed minus 6x squared minus 2xy. And finally, I have dy over dx equals this. It was a very good example. Good pick. So the top will be, of course, y cubed minus 6x squared minus 2xy. And of course, the denominator is x squared minus 3x minus y times y squared. There's nothing you can do here. This is it. I don't like the way this looks with that raised dot, so I'm going to erase it and put y squared closer. Yes, please.
So when you're moving everything to the other side,
Yes,
what if you moved all the dy dx's to the other side?
same thing. Then I will be looking at the equation like this. X squared minus 3x dy over dx. Same thing. No different.
So for the part where
It's still linear. It's a linear equation, dy over dx. Sorry, yes.
the
Sure.
part where it was like that, where you're initially finding like the x squared times dy dx, you say that is at like the very
This one?
yes, like you're saying because y is a function. I don't understand like what you mean when you determine to put dy and dx next to it.
Okay. So here's, let me show you two examples. When I differentiate y cubed, I get 3x squared. When I differentiate the function to the third power, denoted by anything, by y, by h, by you name it, any function to the third power, I have to write 3 times f squared times f prime. That f prime is denoted by dy over dx instead of f prime.
Okay.
So when I'm here to differentiate y cubed, so when I differentiate y cubed, right, so I use the product rule. The first function prime is 1 times the second function plus. I copy the first function, and now I differentiate the function to the third power. I have to have 3 y squared dy over dx. So that's how I have 3 y squared dy over dx. Better? It's a function. So I know it's confusing, but just don't look at it as y. Just say it's a function. Yeah. It can get a little confusing till you get used to it. Okay, so now we know what implicit differentiation means. I think we should choose another, and then I will show you the inverse trig functions and their derivatives. Only 3 of them. No, very easy. I'll make it very easy. Just the 3 most important ones. I promise. Okay, I have to calm Jed down. Yeah, he says, just kidding. Good, just 3. I promise you, and 2 of them are very similar. You're not going to have anything that is beyond that. The basic ones, formulas will be given to you if I ask you anything, and I will not. I test the basics, the basic topics. Okay, are we interested in another one, like finding the equation of the tangent? Who knows what? Maybe you want another one. Everything is, the next section is still implicit differentiation. You'll see.
Sure, let's find the
Which one?
25.
We want to look at 25. Very good. So 25 on 215. 25. Okay, so we have y. Sine 2x equals x cosine 2y. Use implicit differentiation to find an equation of the tangent line to the curve at the given point. And here's the given point. Pi over 2, comma pi over 4. Perfect pick. And I'm going to say solve for y, and you'll say, did you lose your mind? And then I'll say, no, I'm just kidding. So since we are asked to find dy over dx, this clearly tells us not to treat y in any other way but as a function. Okay, so then now, when I differentiate the left-hand side, I have to use the product rule. When I differentiate the right-hand side, I have to use the product rule. When I differentiate y, I get dy over dx. It's a function. I don't have it. I have to write y prime, but I will write dy over dx. Multiply by the second function, and then plus the first function, and now we differentiate sine 2x, which we know how, and it's not a big deal. Sine 2x prime will be from the outer to the innermost. Sine prime is cosine 2x, but times, now I reach the innermost. 2, indeed. Excellent. Thank you. the right-hand side, x prime is 1, so I have cosine 2y, but plus x times, and now I have to differentiate the outermost, which is cosine, and then the innermost, which is 2y, and then the innermost, which is y. So, actually, good pick, Sean. Very good. Yes. So when we differentiate cosine 2y, we have to write negative sine 2y times. Now I have to differentiate 2y, which is a constant times a function prime. Right, so I differentiate 2y to get 2 times, very good. Some problems are more straightforward, some others are really intense. So maybe we should do this one more time. Let's go through it one more time. So I differentiate a function that I don't have. So it must be the symbol dy over dx times the second function plus the first function times the second function prime. When I differentiate the outer, I get cosine. When I differentiate the inner, I get 2. Equals. The first function prime is 1 times the second one plus the first one times the second one prime. I have to differentiate the outer, so I get negative sine 2y. Now I differentiate 2y, and I get 2. Now I differentiate y, or I should say just 2y prime is 2 times dy over dx. Maybe I should just say that better. So when I differentiate a constant times a function, I have the constant times the function prime. So this specifically is c times f prime, which is c times f. C times f prime. Okay, now I have to clean it up, organize it. I realize that I have the variable in 2 spots. It doesn't matter to me. If you want it here, that's fine, and then move it to the other side. But let's clean it up in one row. See if I can make it. You can. But it's doubtful if I can. dy over dx plus 2y cosine 2x equals cosine 2y minus 2x sine 2y dy over dx. A miracle has just happened. I fit it in one row. Okay then, so now the reason why I would like in this case to put this here is because if I move it to the other side, I would have a negative. Both terms would be negative, and I don't want that. Okay, so I have sine 2x plus 2x sine 2y, and everything multiplied by dy over dx, and that equals cosine 2y minus 2y cosine 2x. So I think it's clear now that I moved this term to the other side and also factored out dy over dx. I kept cosine 2y and I moved this term to the other side. And this is linear. This is a linear equation. I know it looks anything but it's just a linear equation in dy over dx. So then dy over dx will be a ratio. This over this, of course, that's the coefficient of dy over dx. Is this enough? No. No, we are asked to find the equation of the tangent line to the curve at a given point. So here's how I evaluate now. Just draw a vertical line, and I write x equals pi over 2 and y equals pi over 4. This is what I was explaining, but I couldn't do it because I made up that equation a few minutes ago. So I couldn't plug it in. I couldn't give you a number because or the ordered pair because I didn't check anything. So I didn't have that. But now we do. So then, let's evaluate. So 2 times pi over 2 is pi. Cosine pi is negative 1.
Wait, pi over 4.
It's pi over 4. I'm sorry. Thank you. 2 times pi over 4, that's even better. That's even nicer. Thank you. It's 0. So 2 times pi over 4 is pi over 2, which is 0. Excellent. Thank you very much. Thank you for keeping an eye on me. Good. Minus 2 times y. Okay, I'll pay attention now. Pi over 2 times cosine times 2 of 2x. Cosine 2 times pi over 2 is cosine pi, which is -1. So I'm going to change the sign in front. So 2 times pi over 2 is pi, but cosine pi is -1. And we had -1 times, yes, times pi over 2. Correct. Okay, sine 2x. So 2 times pi over 2 is pi. Sine pi over 2 is 0. I'm sorry, I meant to say pi. Sine pi is 0. And then plus 2 times pi over 2, which is pi. And then sine of 2 times pi over 2, 2 times pi over 4, which is pi over 2. Sine pi over 2 is 1. So then the numerator is pi over 2. The denominator is pi over 1. So I have pi over 2 times 1 over pi. I simplify, and I get 1/2. So this is the slope of the tangent line to the graph of whatever that is at pi over 2, comma pi over 4. So now y minus y1 equals the slope times x minus x1, where the slope is 1/2. X is pi over 2, and y is pi over 4. We're asked to not just find the slope of the tangent line to that graph, but also determine the equation of the line, of the tangent line. Any questions? Any questions? Oh, I can finish it up. I should have, yeah. So we have y minus pi over 4 equals 1/2 x minus pi over 2. So I have 1/2 x minus pi over 4. Oh, that's really nice. But with plus pi over 4, goodbye. So this is it. Right. 1/2 multiplied by negative pi over 2 is negative pi over 4, but I have a negative pi over 4 on the left and a negative pi over 4 on the right, and they go away. So the equation of the tangent line to the graph of whatever that was at pi over 2 comma pi over 4 is y equals 1/2 x. I know we have 6 inverse trig functions, but I only insist on 3 and very, very decent derivatives. So arc sine prime is 1 over the square root of 1 minus x squared. Arc cosine prime is -1 over the square root of 1 minus x squared. And arc tangent prime is 1 over 1 plus x squared. The reason why I insist on these is because you're going to see them at every step of the way almost. I'm exaggerating a little bit. In Calc 2. In trig substitutions of integrals, etc., etc., etc. You will not be able to get away from these 3 functions. The rest, not that much. So I insist you remember just these 3, nothing else. These are the trig, the derivatives of the inverse trig functions. We know all 6 trig functions, all 6. We know there are 6 inverse trig functions, but I'm only asking you to remember these 3 as their derivatives. And now please choose anything you like that does not have the other ones. If I put, which is not going to happen, I will give you the formula. So it's not going to be the case. Everyone can look up a formula and present. And these are the basic ones that I'd like you to master. Anything you like with arc sine, arc cosine, arc tangent? Okay, 1, 2. I'm going to start with 53, and then you have your second chance in a minute. 53. Page 216. You understand that this is really not that big of a deal, right? One is positive and one is negative, identical. And this is the square root, and this is 1 over 1 plus x squared. Okay, so in 53 we have a function denoted by g of x, uppercase, the square root of 1 minus x squared. And this is multiplied by r cosine. Now, we do know that there exists another notation that I really don't care for, but we have to remember that there is another notation which does not mean 1 over sine. It's just the inverse function of sine. The same thing is cosine inverse, which does not mean 1 over cosine. It's arc cosine. And of course, for this one, tangent inverse. I prefer arc sine, cosine, and arc tangent because it's easier for me to type. I don't have to put a power, right? So as you know, these are in the graphing calculator. Here they are, right, with the second key, right here. Sine inverse, cosine inverse, tangent inverse. Okay, activated with the second key. These are the inverse functions, not the derivatives, right? Just the inverse functions. Okay, perfect. So here we are. We are asked to differentiate this function, and of course we have to treat it as a product. It's a product of two functions. The square root is a function, and the arc cosine is another function.